So we're going to talk today about what the VSM is and how it works a little bit. Then we're going to mount a sample and we'll do a test run for a magnetoionic measurement. So this is a VSM in our lab, and the way it works is you place a sample in the center here. You apply a magnetic field and you measure how the magnetic moment in the sample changes during this applied field operation. The key components are the coils, which is these two here. They're essentially huge windings of coil of copper, water cooled to keep it cool because it gets quite hot at very high fields. You have the drive head, which you will mount a rod on with your sample, and it will vibrate at a fixed frequency, in this case 60 Hertz. And then here you'll have two pickup coils, or four pickup coils, which register the variation in the magnetic field via the induced current in the pickup coils. And it will separate out the magnetic moment signal by using a phase lock amplifier to select out the variation due to just your sample. So let's go ahead and mount the sample and mount it in and see what happens. So to do something a bit more interesting, we're going to do a magnetoionic experiment. So we're going to mount a cobalt oxide film in an Eppendorf and fill it with PC, and then apply a bias and see how the magnetization changes. This is our sample. It's cobalt oxide sputtered on top of a copper underlayer, similar to the one you saw in the sputtering video. What we're going to do is we're going to take this sample and then connect it to a copper wire that we solder onto the copper region as a contact. And then we will solder another wire, a platinum wire, that we're going to grab from this set of platinum gauze, and then we'll form a working electrode and a counter electrode. So here's the quick and dirty assembled piece. So we have our oxide film, we have one wire that has been soldered to the copper contact, and then we have our little platinum wire that's been twisted around and soldered onto another wire. That forms the working and counter electrodes respectively, and then we have them mounted using a kind of glue here just to keep them separated by about 3 millimeters. And if I rotate it, maybe you can see that there is a separation between the counter and the working electrode. And this is the final product that we're going to use to mount in the VSM. We have the as prepared counter and working electrode mounted inside an Eppendorf. We filled it with propylene carbonate, which is a polar liquid that we're going to use to bias our film surface. And then I've mounted this and centered this on a quartz rod, which we will use to mount in the VSM. And I've taken the two wires and just wound them around. So let's go ahead and take this and mount it in the VSM. Okay, so now we have the sample mounted inside the Eppendorf on the rod. I'm going to mount it onto the head here, and the orientation depends on what you intend your measurement to do. In my case, I want to measure in-plane measurement, so the film is oriented like this. And I've attached it to the head, and remember this is the part that vibrates at 60 Hertz to generate the induced current in the loops. And then I'll rotate it down into the sample zone, and then I'll center it inside the coils. So now we're going to start a magnetoionic measurement. For those of you who don't know, we're going to apply a voltage, and this voltage across the two electrodes will drive ions in and out of the sample, in this case oxygen out. And we should see an increase in magnetization because of the lack of oxygen and more metallic cobalt present. So I've hooked up the two electrodes here. We've got the working electrode here connected in the red wire, and we've got the counter electrode hooked up to the black wire. And what we're going to do is we're going to apply a bias of negative 10 volts. So let's go ahead and start that. See the negative 10 volts, and then we'll see some nominal current flowing through the sample. So let's see what the magnetization looks like. Okay, so now we're doing our measurement. You can see now that the sample is vibrating up and down, and as it's vibrating up and down, it's inducing some current into the pickup coils, and that's what we're reading off as the magnetic signal. If it's non-magnetic, then nothing should happen, so you should get zero magnetization. And if you have some magnetization, like an iron or typical things like this, you should see a pretty distinct loop. So let's see what this sample gives us as prepared without applying any voltage first. Here's what the hysteresis looks like for the as prepared sample. That is, it's not been treated at all with any voltage bias. As you can see, it's got pretty much no magnetic signal after we've slope corrected for the background. And I'm showing you a range between 10 and negative 10 kilo-Oersted. And we'll see how that compares with the sample after it's been treated with voltage. Here is what our sample looks like after it's been treated with voltage. The blue line I've left in as reference what it originally looked like. And the red one is the loop as measured during the voltage application process that you saw me set up. This loop takes about 25 minutes to complete, and you'll see the hysteresis loop shows an increase in magnetization over time up until it reaches over 200, nearly 300 micro-EMU, showing a clear appearance of a magnetic signal, evidencing that we removed oxygen from the sample.